Hi everyone. So I'm Ami from Hebrew University. I'm going to talk about the geodesic convexity and covariance estimation. So I'm going to start with what is convexity, which I hope you all know, then continue to geodesic convexity, and then show some applications. Now, I did my master's with Chagit. The main lesson I learned is this triangle. I think Chagit didn't call it a triangle. I think she called it a blanket or something like that. But the main idea, that's what I got from 2 years working with Chagit, was that statistical signal processing is about these three things: accuracy, robustness, and complexity. And there's a trade-off. We can't win them all. And then I finished my master's and continued. And since then, I tried to kind of understand this trade-off using convexity. So what is convexity? A convex function, I guess everybody here knows what it is. This is a convex function. If you take 2 points, you draw the line between them. If the function is under the line, it satisfies this inequality, that f over the line is smaller or equal to the line connecting fx1 and fx0, then the function is convex. And why is that good? Because local minima are also global, and finding local minima is very easy. Okay, that's the main idea. And how is this related to Chagit? Well, because there are different ways to do it, but my way to solve this triangle is using convexity. And I think through the last years, I kind of tried to understand this trade-off using it. So for me, accuracy is finding the global solution, if it's maximum likelihood or some other problem. I usually take problems in statistics and transform them into optimization problems, and then I want to find a global solution. Convexity allows me to do it. Then people here mentioned, Joseph mentioned asymptotic performance and reaching the camera. What I'm today in the last years, what we are more, in many problems, we are more interested in non-asymptotic performance. Non-asymptotic performance, the way to do it today, one of the leading ways is using convexity. Okay, so that's about accuracy. Complexity is quite obvious. For me, the problem boils down to taking a problem and transforming it into a convex form. Once it's convex, it's tractable. Otherwise, I usually give it to my students who are sitting there. When the problem is not tractable, what we usually do is convex relaxation. And today we even know how to do these things in large scale. And then comes robustness. And today there are many ways called robust optimization to take care of this issue. And I'm not going to talk about that much today. So that's why I think convexity is one solution to this trade-off. And as Yuval mentioned, it's also a special case because the triangle is convex. But the problem is that there's only so much functions which are convex. And that's a problem because we need to write many papers. So I had to find another form of convexity that people didn't know before. And that's geodesic convexity. And I hope I will convince you that it's interesting today. So here's a very nice slide, which most people don't know, but it's very simple. Here is the usual convexity inequality, okay, that f over the line is smaller than equal than the line between the 2 points. And everybody knows that this inequality gives you convexity and that every local minimizer of f over the region is a global minimizer. What most people don't know is that there is no need for this qt to be the line between q1 and q0. It can actually be any kind of curve that takes you from q0 to q1. Doesn't have to be line, can be curved. The region you're working in doesn't have to be convex like a triangle, but can be non-convex, but connected, okay? The only thing you need for this property to hold is that for any 2 points inside this region, you need to define some curve that goes between them, and that this curve, I'll call it qt, that's a function. The only thing that is important, it has to be continuous, okay? That when you take t equals 1, you get q1. When you take t equals 0, you get q0, and you need to go between them. And then in 2 lines, you can prove that if this inequality holds, then any local minimizer is a global minimizer. The question is just finding this curve, okay? Which curves are interesting? And that's what I'm going to try to show. Now, this thing, I didn't invent it. People knew about this long ago. Okay, in 91, Raptite did it. There's some work in 2004. Bental in the Technion have many works on it. It's called convexity on arcs. But all of these papers are very mathematical, very abstract. They give you exactly these properties, but they don't tell you which QT you should find. You should use, actually. Okay, and they're just completely abstract.
Just clarification.
Yeah.
So is QT independent of Q1, Q0? Is it a single QT or actually every pair?
No, it's a vector parameterized by t. The only important thing is that when t equals 0, you get then qt with the t equals 0 is equal to q0, and when t equals 1, you get q1, and it just goes between them. Some kind of path between them, parameterized by t, and t goes between 0 and 1. Just like a line, but it doesn't have to be a line. It has to be some continuous path. Now, I call it geodesic convexity because I'm actually going to use geodesics. I'm going to use the minimal line on some kind of metric, but that's completely not important to get this property or for anything I will say, okay? The only thing that the geodesic is important is just it's a good guess for which curve you should use. Okay, and the proof of this is just 2 lines. Okay, so let me give you an example. How many people here have heard of geometric programming? Okay, so geometric programming is something I think most people in communication know. It's very famous. It's a trick. Everybody knows that linear programming is solvable. That's when you minimize linear functions. Geometric programming is a trick to do the same when you want to work with products, when you want to work with polynomials. Okay, and how do people do it? They make a change of variables, okay? It works only on positive scalars, that's the domain. And they make a change of variables. They say, if you're going to work only with positive variables, then you can replace each one of them with an exponent. And then you get a regular convex problem, and you can start solving things like this using a change of variables. And that's well known. People have been using it all over. What they didn't say, and it's not really important, but it's just a different way of looking at it, is that you can do the same thing without a change of variables by just noting that these functions here are not convex, but they are geodesically convex over a different path. Instead of working with the path that is t times q1 plus 1 minus t q0, you need to work with the geometric path between them, the geodesic. And this is this one. So that's not very new. People knew that a long time ago. They didn't use my interpretation. This interpretation is new here, but this thing has been very useful in many places. They use it in power control to solve problems like this. Okay, they use it in circuit designs. The important thing is you can solve something like polynomials, they call it polynomials, with positive variables. So here the variables are powers, which are obviously positive. And here it can be width or length of transistors. And they did a change of variables, and then the problem became convex. What I just told you is something new, that they didn't actually need to do the change of variables. The problem was just from the beginning, they were not convex, they were G-convex. But big deal, who cares? Okay, the important thing is that local is global. And finding locals, that's easy. Now, I know this statement is not exactly right, but let's assume it is. Okay, so now, this is where I come in. I looked at this thing and I said, okay, if it works with positive scalars, let's do the same with matrices. So I wanted to generalize geometric programming to work with positive definite matrices, okay? Oh wait, one more thing I should say here. You see here, I told you at the beginning, linear programming works with linear sums, and this works with products. Why product? Because the exponent, change of variable, transform a sum into a product, okay? Remember that. Okay, so now I want to do the same with matrices. What do I need to do? I need to find some kind of generalization of this geodesic between positive scalars to matrices. And this ugly thing here is exactly that. Okay, if you take, this is a matrix exponent, it means take the eigenvalue decomposition and just take the eigenvalues to the power, okay? It's kind of ugly, but it's very easy to see that if Q0 and Q1 here were scalars, then this would boil down exactly to the equation we had before. Okay? And it's also, it's known that this is something called the geodesic, the shortest path in some kind of metric, which is not very interesting for us, between Q0 and Q1, which are both positive definite. Okay? Now, I said, okay, let's look at this geodesic, and let's see which kind of functions are convex, are G-convex over this thing. And these are the kind of functions that I got. I could solve like powers, I could solve log determinants of sums. It can be of Q. Q is the variable here. It can be with Q, it can be Q to the -1. Now, not all of you that think that log, you know, that log det is a concave function. I just told you the opposite. Log det is also a convex function. Because you all knew you can maximize it, now I tell you you can minimize it. Okay? But the unfortunate thing is I don't have a change of variables like taking an exponent that will really convexify it. But who cares? The important thing is that local is global, and finding locals, you're just going down. Okay? You do some gradient descent. Okay, now remember what I told you, that in the scalar case, sums becomes products. The same thing has to happen in the matrix case. The only question is, what is a product? There are different kinds of products in the matrix sense. Apparently, one of them, which I'm using here, is the Kronecker product, where you take two matrices. The Kronecker product of them is this thing. And indeed, if these two were positive definite, this will also be positive definite, and we'll soon see some applications to it. Okay. So now in the rest of the time, this is very short for this talk, but I'm just going to go show you two examples of how this can help us in life. So I like working about covariance estimation. The problem is very basic in statistics. It's the easiest problem after mean estimation, which everybody knows. So you have a vector x, p-dimensional. Let's assume we know the mean because it's easy to estimate. Okay, and it has some covariance which we don't know. We've got IID realizations of x. And the problem, we want to derive some estimator, some function of our measurements to estimate sigma, to be close in some sense. What do people who learned with Hagit do when they get such a problem? No, they first do the Camera bound. But I was a bad student, so there will be no Camera bound here. I'm the only one in the audience here who doesn't do Camera bound. I skip straight to the maximum likelihood. And okay, so what? And then I need to decide whether I can solve it or not. And the thing is, it's very easy when X is Gaussian and there's no structure and when you got lots of samples. Why is it easy, everyone? Because it's convex. Otherwise, it's very hard. Why is it hard? Because it's non-convex, which means we start going down and we get stuck somewhere. Okay. So now I'm going to show you two applications which are not convex, very popular, but they are geodesically convex. So the first one is robust covariance estimation. The Gaussian case is the easiest and most famous example, but the world isn't always Gaussian. And then there are lots of alternatives. Okay, there are millions of them. Most of them, some of them are just generalization of the Gaussian case to more general distribution. Some of them come from robust statistics. So you've got elliptical distributions, spherically invariant random processes, compound Gaussian, multivariate student, multivariate Laplacian, generalized Gaussian, lots of them. And people have been solving these things for like 20, 30 years now. And all of these maximum likelihood optimization, all of them are non-convex. Yet, surprisingly, very, very smart people succeeded to show that they know how to solve them. Okay, it starts with Haber, Tyler, Marona, and then in the last years, I'll show you more reference. But basically, all of these distributions, people know how to solve them. They have very simple fixed point iterations that look like this, all kinds of weighted sample covariances. Okay, this is just a weight here. But these are iterations, and they know that this iteration will solve it. Now, how do they know it? They first did it by simulations, and then they have 10, 15 pages of proofs showing that this specific iteration finds the correct solution, the global one. Now I'm not going to go over all the references, but there are like dozens of papers here really starting with Tyler, who introduced these things. Then people did analysis, generalization, Bayesian priors, regularization. The last year is more Laplacian, MGGD, complex elliptical. They did it to almost everything I wrote up there. And the solution was always, we can always do some fixed point iteration. We work very, very hard. And these are really smart people. I have here Ilya, who tried to go over the proofs. He can testify that it's really, really hard. But they always succeed to prove that every local is global for these fixed point iterations. I think you got my idea already. Why did they succeed? Let's take, for example, look at Tyler's estimator. Looks something like this. There are lots of variants of this. The important thing, it's non-convex optimization, but we have over 25 years of people proving that they know how to solve it. The reason is very simple. It's not convex, but it's geodesically convex. And how do you know that you found something smart and big? Somebody did it before you, and you go back to the literature and you find in some mathematical journal that nobody ever read somebody who did it. And now we have lots of extension, regularization, MGGD, complex elliptical, even graphical models, lots of stuff. So that was one application. And now let's forget about this. People now go to something completely different, okay? This is a different group of people who know nothing about robust statistics. Well, maybe some of them do. But these works are different. They talk about something called Kronecker models. What's the idea? It's very hard to estimate the covariance. Why is it hard? Because if you got a vector of size p, then how many parameters are there in the covariance? Roughly half p squared, right? That's a lot of variables. So when you start working in big vectors, you can't do it. Then you need to put some low-order model. You don't really believe that model, but it's a bias-variance trade-off, which Hagit told me about a few years ago. And one of the most standard things is to impose a structure, which is called the Kronecker structure. The idea is, instead of modeling vectors, we model a matrix, which is IID, and you have two smaller covariances of the size of the rows and columns, which color it from the left and the right. And this makes a lot of sense. For example, it can be in communication when one side is the transmitter, one side is the receiver. It can be in Netflix when the American guests of us choose their movies. We don't have Netflix in Israel yet. So one of the models they use is one side is the product, one side is the customers. And again, we don't really believe that the movies and the customers behave like a conical model, but it's a good approximation of low order. And surprisingly, people did it already in 1993. They said, well, the problem is not convex, but let's do the famous flip-flop algorithm. Solve for Q1, then solve for Q2, then iterate, and hope to get a global solution. Lots of papers, I'm not going to go over them. Basically, with lots of work, they succeeded to show that this always solves the problem. Okay? Well, we don't have time for this. The idea is lots of application, lots of difficult theory, but everything is specific and very hard to follow and generalize. I think you got the idea, right? It's not convex, but it's geodesically convex. Remember what I told you about in scalars, sums, when you take a change of variables, transform into product? In matrices, sums turns into Kronecker product. So this is the Gaussian distribution, okay? It is convex in the covariance. When you put a Kronecker product here, geodesic complexity is preserved, and we have this theorem that the negative likelihood is jointly G-convex in everything, and it's no wonder everybody succeeded to do this. We, of course, have lots of generalizations and examples, but I'm not going to go over it. The main idea is that every local minima is global, and from here, you give it to someone who knows how to solve local problems. To conclude, because we really ran out of time, so statistical signal processing and convexity, we have this trade-off. I found that one way to do it is using convex optimization in the middle of the triangle. Sometimes it's better not to use lines, but curved geodesic. Geometric programming is one example which everybody knows, but they always do it using a change of variables. You don't need the change of variables, and a change of variables doesn't always exist. All you need to do is find the right path, showed you some applications, and the take-home message is if you always find a global solution, then maybe it's G-convex. And that's it. And I think I even saved you some minutes.